who are the users of this chip?
It's mainly implemented in the multi-core processors. So basically,
so each node is a
router.
Complete processing unit.
Each node is a complete, yes. Each node is a complete processing unit, and then we have routers that are implemented into them. Another algorithms that we have to take a look at is the n-random walk. The n-random walk algorithm is a non-deterministic algorithm, meaning that as a path, as we said in the XY algorithms, the paths are deterministic. Here the paths are completely dynamic. Anytime you're routing a packet to a destination, from a source to a destination, it could take a multiple paths, different paths each time you route it, depending on certain parameters. The n-random walk is a partial adaptive algorithm, and it could be a fully adaptive algorithm depending on the number of random walks that we choose. And of course, each number has its positives and negatives, which we will see soon. And as I said, it's based on the idea of injecting an n number of packets to the network. And also uses the Manhattan distance and a multiplicative factor to choose the outgoing channel. The idea here is every time you receive a packet, let me step forward here. So every time a router receives a packet, it should calculate the probability of which outgoing channel it will choose to forward it. The way that it does that is first by using the Manhattan distance between the source and destination. And the shortest distance is the one that has the highest probability. The lower distance is the one that has the shortest lower probability. And what I mean by probability is the channel with the highest probability is the one that the packet will get forwarded using it, as long as it's in the direction to the destination. And that doesn't mean that we're ignoring the other outgoing channels. We're not ignoring them, but we might use them later, depending on the load that's on that outgoing channel. And after that, after we use the Manhattan distance, each outgoing channel, the one that has higher probability will get assigned a higher factor, and each one that has the lowest probability, and it's also not in the direction of the destination, will be assigned a factor of 1. So suppose that we want to send a packet from this source, IPA to IBP. After calculating the Manhattan distance, we figured out that this outgoing channel, the north one, has a probability of 6, and the east one, sorry, has a probability of 5. So this means and the fact that the west one and the south one has a lower probabilities. So we assign them a multiplicative factor of 1, and those guys have a higher multiplicative factor, which is actually 6. Then we do the average, so we calculate all the factors and then divide each probability by that factor. And after doing that, we can see that we have 6, 5, and then 1, 1, that's 13. So basically speaking, the north outgoing channel will have the highest probability, and this is what we're going to use in order to route the packet to the destination. The reason why I said the outgoing channels that has lower probabilities are not going to be ignored, because sometimes we need to use those in order to create multiple paths to the destination, which will help us balance the load to the destination. So yes, that n-random walk can provide us with a minimum or non-minimum path, but it also helps us to create some load balancing on the network, so we help lower the congestion rate there. Source routing algorithm. It's a fault-tolerant algorithm The good thing about any source routing algorithm, about this source routing algorithm, is that there is no periodic routing tables management. If we just have an analogy to the internet that we use these days, and we know that we have source routing also schemes, the fact that, we also know that there's a periodic update that needs to be sent every X amount of time. In network on chip, we do not have this periodic routing management. And also, routes are cached, which means that once we figure out the route, we can cache it for a specific period of time so we can use it in the future. This will minimize the overhead. The source routing uses a route discovery and route maintenance protocol. And what we mean by that, an example would tell us what does that mean. So suppose that we want to route a packet from router 1 to router 9. Router 1 does not know how to route this packet there. So what it will do is basically flood the network with this packet. So suppose that in our analysis we're going to take this route, 2, 3, 6, 9. Router 2 does not know how to get to 9, so it will flood it again. And thus router 3 until it gets to router 6. Router 6 knows how to get to router 9, so it will send an information back to router 3. Router 3 will cache this information. Will say, if I want to get to 9, I should go through 6. And then send the information back to 2. Router 2 will cache the information again and send it back to router 1. Every time router 1 sends, or any router sends a request, it will be tagged with a specific ID. So the router knows where did it come from. And the first request that gets to router 6 is the one that will be served. Any other request that would reach, will come after that will be silently dropped. And that, intuitively, that tells us something. That if I'm routing a packet from 1 to 9, and then routing a packet from via 2, and then routing a packet from 1 to 9 via 4, and the one that's routed via 2 is the one that's getting there first, that tells us two things, intuitively. It's either taking the shortest path, or it has come along the less congested path. And that makes sense for me to use it because it got there faster, and this is my main objective in any network. And any other thing that came after that, it makes us drop it because it didn't make it there for very fast. And that's what we mean by route discovery. Route maintenance deals with this thing. If I'm routing a packet from 1 to 9, going via 2, 5, 8, 9, or sorry, 6, 9, and then the link on 5 just breaks down or goes dead or it's really congested. When 5 is sending the packet and it's not getting acknowledgement back from 6, it will send it for 3 times, and after that, when there's no acknowledgement, that tells, just like in any network, it tells 5 that there's a problem going on this link. Route maintenance means that now router 5 should flood the network with this information, saying that the link between 5 and 6 is dead, and all the network will update, or the routers will update their routing tables by flooding the network just to accommodate this fact. So this is what we mean by routing maintenance. Disadvantages for source routing is the fact that we have a routing table at each node, and in each node will store the full path between itself and any other destination. So these are really huge tables. And also we have a setup time latency for the fact that we have to use the routing discovery protocol to set up a path between a source and a destination. And also we will have excessive delays in this case where we have a broken link, because it takes a while for us to figure this out, depending on the timers between each send, the 2 successive sendings, and then the other overhead will be flooding the network again to update routing tables. The final algorithms that we will take a look at is the table routing algorithm, which is a fully adaptive algorithm, which means that anytime we have a problem or a fault, we will fully go and route that fault. It's analogous to link state. And it's also analogous to the source routing algorithm. The only difference is the fact that in source routing we store the complete path between the source and destination. In table routing we store only the next hop. And it's always provide us with the minimum path to the destination. It provides us also with load balancing. And as I said, there's always a minimum path between the source and destination. A quick look into how does it work. So suppose we have our source is router 7, sending a packet to router 1. Router 7 will flood the network again. And then it will receive responses from all of those routers that it's connected to, which is 4, 6, 8. It will take into consideration only the minimum path and drops back any other response that has the higher path into the destination. Router 4 will do the same again now, flood the network, get the destination, get the results, and picks the minimum path to the destination. And finally, our destination will be 741. As I said, they provide us with a load balancing. It's a fully adaptive, so if you were sending a packet from 2.0 to, let's say, 2.4, but we have these three routers are dead, so the algorithm will find a way around the fault, because now each time the router 2 will send a packet to the next router, and it doesn't get a response back. Sent it for 3 times, there's no response. So now it will take a detour into the destination. And I'm sorry that I'm running really quick, but I'm running also out of time. For our evaluation here, I use a NERGM simulator to simulate a network on chip. It's a cycle accurate simulator designed by using System C. Implemented the X, Y, and N random walk, and excuse my typo here, I did a negative first instead of the random tables algorithm, logging tables algorithm. Use the 9x9 mesh network. The reason for choosing 9x9 is a lot of literatures, or we can say all of the literatures use 9x9 mesh. Because why do they use 9x9? It's realistic. Most of the network on chips that we have now are even smaller than this. And it's not even, so it's bigger than what we have these days, but it's not really big because we need a decent size of a mesh to figure out that our scheme, whether it has problems or not. We use different injection rates.
What is the typical size?
These days?
Yeah.
These days, I think there's a 2x2 is the major one that's being used.
Oh, okay.
But for simulation, and if you want to evaluate any algorithm, 2x2 does not generate enough paths for you to figure out the faults that you have. Different injection rates, different fault rates. We use a constant burst rate, which means the time between sending each 2 successive packets are always constant. My total simulation time was 3,000 nanosecond. But let me be more accurate here. What I actually used for these different schemes was I sent 3,000 packets actually, and the time between each 2 packets was 20 seconds. So it had higher simulation time than the 3,000 nanosecond. The source and destination was between 0, 0, and 8, 8. And I measured latency, energy, and arrival rates. If we take a look at the experiment results that we have here, so as I said, different fault rates, and here's the arrival rate. And at a 0 fault rate, all of them had a 100 arrival rate, which is intuitive. If we had a 1% fault rate, most of them function, still they were functioning really well. So we can see that for the one random walk is the one that functioned really bad, but then after that it comes the 2 random walk. But still, for the 8 random walk and negative first, and even XY algorithm, they're still functioning well. As we increase the fault rate, of course, performance and the arrival rate drops down, And what I'm really interested in is at under 20% fault rate, we can see that of course 801 is still functioning the best because now we randomize the path, so we're creating more paths toward the